The von Neumann architecture can support several paradigms to construct programs for digital computers.
The closest paradigm to the fetch-execute cycle is called imperative programming.
Imperative programs are analogous to a recipe for cooking.
These types of programs define data structures and variables that hold values.
Such definitions could be considered the ingredients.
Then, a sequence of commands specifies what to do with the ingredients.
Running the program executes the commands in order, each instruction followed by the next in the list.
Note that the program counter always moves to the next instruction in the fetch-execute cycle.
However, if the language to describe algorithms only allowed to build sequences of basic instructions, the possible algorithms would be limited.
In particular, if the only way to compose basic instructions into a more elaborate behavior is to organize them in sequence, the computer would be like an arithmetic calculator.
The theory of the foundations of algorithms says that being able to select the course of action is necessary to describe algorithms.
In this theory, selection says that the algorithm operator can inspect some condition and, according to that, continue with one set of instructions rather than some other sequence of instructions.
The idea of selecting a course of action according to the status of some condition is so common that it appears in popular visual representations of processes such as flow diagrams.
These are also called flowcharts, with visual elements describing a process.
Boxes are usually for commands, and an arrow represents sequencing commands.
The arrow starts on the predecessor and finishes on the successor.
But flowcharts also include the possibility of the decision represented by a diamond shape.
The possible ways the flow can take depend on the result of the question.
For example, we could have a description of a process that, given a positive integer, determines whether this number would be a leap year.
The construct for making decisions in programming languages is usually called the if-then control structure.
It is called a control structure because it allows the programmer to define the control flow, that is, to alter what would be executed next.
With an if-then control structure, not necessarily the next instruction will run.
Sometimes the next instruction may run, but according to the condition, execution may skip it.
In C, only when the condition is true, after the keyword if, will the program execute the code block of this control structure.
The if-then statement of C is translated or implemented in machine language by the branching instructions of the ISA.
Such instructions test a condition and modify the program counter to a label. The label is typically a position in the code different from the default position of the next instruction.
The most common method is to design the control flow with a flowchart or if-then statement of a C program.
Then, when transforming to the assembler language, we test a negation of the condition because if the condition is false, we must skip the body of the if-then statement.
So the branching instruction in assembler tests what is necessary and sufficient to skip the body.
The translation of the body is placed between the branch and the label ending the control structure because, in an if-then statement, when the condition is true, and the execution of the body is completed, the control continues with the instructions after the control structure.
It is also prevalent to have alternative sequences of code.
Coding alternatives are usually named if-then-else statements, where there is also a separate body of code to be executed for the case when the condition is false.
In this case, the assembly language has to have an unconditional branch to the end of the entire control structure so that the flow jumps to the end when completing the body of the true part.
In assembler, we still test for the negation of the condition.
Still, now the label, in the branching instruction, is for the position of the code corresponding to the else part.
At the end of the else, there is no need for branching because control will flow with what is next.
Naturally, if the else statements can be nested, in theory, with arbitrary depth.
While nested if statements are already complex for human programmers in high-level programming languages, they are even more delicate in assembler.
Another aspect that illustrates the level of abstraction in programming languages over assembler is the evaluation of the condition.
Boolean expressions in themselves can be complex nested Boolean expressions.
Perhaps here is when we appreciate the potent tools that compilers and interpreters represent.